All right, the last part of this section on infinite series, we're going to look at telescoping series. And telescoping series is a series in which most of the terms actually add to zero. They cancel in the partial sums. What happens in each partial sum, some of the first terms in the sum remain, and some of the last terms in the sum remain, but all the interior components of the sum add to zero. So a telescoping series, if you can imagine the old-fashioned telescopes that would extend out as you pulled them, kind of like a pirate's telescope, and then would collapse when you push the two ends together. And so I guess kind of in an analogy with a telescope, the only thing that really matters are the ends of the series, the first terms in the series added to the last terms of the series, because all the inner components add to zero. Okay, let's look at a specific example here. And often is the case when I have a rational function inside of here on the natural numbers. Sometimes I can rewrite those with partial fraction decomposition, and I'll notice when I look at the partial sums that the interior components add to zero. So here's a rational function here on natural numbers, and we learned in a previous section that I can rewrite this as a over n plus b over n plus 1. Notice that n and n plus 1 are linear factors, and they're distinct. So there does exist an a and a b, such that I can rewrite it as a over n plus b over n plus 1, and boom, they do it for us. They don't show us the steps, but that's something that's not too hard to do. Okay, so this expression can be replaced with this equivalent expression. Okay, so now I've got this series of 1 over n minus 1 over n plus 1. Let's just look at a couple of the first things. When n equals 1, I get 1 minus 1 half. That's a typo. That should be minus 1 half. When n equals 2, I get 1 half minus 1/3. There's 1 half minus 1/3. When n equals 3, I get 1/3 minus 1/4. 1/3 minus 1/4. So this was when n equals 1. This difference is when n equals 2. This difference is when n equals 3. So notice the minus 1 half and the 1 half add to 0. The minus 1/3 and the 1/3 add to 0. The minus 1/4 and the 1/4 would add to 0. The minus 1/5, and if I kept going, these interior components would continue to add to 0. The only thing that would exist at the end of it would be a 1, and this last kth term in the partial sum. So a 1 would remain, and 1 over k would remain if this were from n equals 1 to k. Okay, so here they do it explicitly. S sub 1 is 1 minus 1 half. S sub 2 is 1 minus 1 half plus 1 half minus 1/3, so it's 1 minus 1/3. S sub 3 would be all these interior ones collapse and add to 0 except the 1 and the minus 1/4. So if we look at this, S sub k, if you look at the pattern, would be 1 minus 1 over k plus 1. Right? So S sub k is going to be 1 minus 1 over k plus 1. So now I can take the limit of the partial sums as k's go to infinity. The limit as k goes to infinity of this would be 1, right? 1 minus 0, because as k goes to infinity, this denominator is arbitrarily large, and 1 by arbitrarily large is 0. 1 minus 0 is 1. So this series, by thinking of it as a telescoping series, we can easily get at the formula for the partial sums. We get the formula for the partial sums to be 1 minus 1 over k plus 1, and take the limit as k goes to infinity, we get 0. All right, so these are, I think they're kind of fun to do, these telescoping series. Let's look at another example here. Okay, determine whether the telescoping series, cosine of 1 over n minus cosine of 1 over n plus 1 converges or diverges. If it converges, find its sum. So let's go ahead and look at the textbook. They're going to write out a few of these first terms. You know, when n equals 1, I'm going to cosine 1, right? Minus cosine 1 half. Okay, so here's the cosine 1 minus cosine 1 half. When n equals 2, there's still the first 2. But when n equals 2, it's going to be 1 half minus 1/3. So cosine 1 half minus cosine 1/3. Notice the negative cosine 1/2 and the positive cosine 1/2 add to 0. And the only thing that remain are the ends, cosine of 1 minus cosine of a third. The third partial sum, so when n equals 3, you're going to get a 1/3 minus cosine 1/4. So all of these will still be the same, but I'm going to have an additional extra subtraction because of the third. So cosine 1/3 minus cosine 1/4. But notice these are all adding to 0, these interior components. So I'm only going to be left with cosine 1 at the left and minus cosine 1/4. So if you look at the pattern, S sub k is going to be cosine 1 minus cosine of 1 over k plus 1. So taking the limit as k goes to infinity, this doesn't change. But I'm going to get minus cosine of 1 over, well, this would be infinity, but 1 divided by arbitrary large value is 0. The cosine of 0, as we all know, is 1. So we're going to cosine 1 minus 1. So the limit of this particular series is cosine 1 minus 1.